Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show finite element analysis of a simply supported beam with uniformly distributed load. Let us see the statement of the problem. A cantilever beam AB carries a uniformly distributed load of 1.5 kN per meter over a length of 1.6 meter from the free end. Draw the shear force diagram and bending moment diagram of the beam using ANSYS mechanical APDL and compare the results. You can see this is the beam. It is fixed up the left hand side, and from left hand side at a distance 0.4 meter we are providing a uniformly distributed load of 1.5 kN per meter with a span of 1.6 meter. We need to find out the shear force and bending moment diagram, and that to be compared with the results obtained here itself, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. Okay, first of all we need to create a directory, and in that directory we need to save everything, and next to that we need to create a title of this one. Let us change the title to this one as FEA5. We change the title as FEA5. Done. To see the title, let us click plot replot. It will show the title at the lower left corner. Done. Now first of all we need to see what type of analysis it is, and it will be obtained from preferences. So definitely it is a structural analysis. Next to that we need to provide elemental properties, and that will come from preprocessors. Element type, add edit delete, that to be added from here, and we are considering beam with 3D finite strain with element type reference number as 1. Okay, now from options we can change the element behavior from linear to cubic. Okay, done. Now we need to provide material properties, material models, structural, linear, elastic and isotropic. Isotropic means material property remains same in all directions, and modulus of elasticity will be 2 into 10 to the 11 Newton per meter square, so it is 2E11, and Poisson's ratio will be 0.3. Done. Let us close it. Sections, beam common sections, and for all cases we are considering the beam is made up of square cross section of height equal to 0.01 meter and width also 0.01 meter, right? So we are providing breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. It's complete. Now we need to start modeling, and better to create key points in active coordinate system. So create key points in active coordinate system, and we know that total length of the beam is equal to 2 meter, and we are providing uniformly distributed load at a span of 1.6 meter, and it is 0.4 meter from the left hand side. So first key point we are creating at origin. Apply. First key point is made. Next one will be at a distance of 0.4 meter from origin, so 0.4. Apply. Done. Now the third one, it will be 2 meter from origin. Applied. Done. Now one thing we can do for orientation of this beam, we can create one extra point at any specific location. Let us point that orientation key point at x equal to 0 and y equal to -1. Okay, done. Now the key points what we made, that to be connected in the form of lines. So we can create lines, straight lines. Let us join key point 1 and 2. Done. Now key point 2 and 3. Done. Okay, next to that we need to start meshing, and for meshing first of all we need to start with mesh attributes, because the orientation point to be also considered for these mesh attributes. So mesh attributes, picked all lines, and in this case we are considering the orientation key point also. Okay, now let us select that key point 4 for orientation. Done. Now we need to start our meshing, and it will start from size controls, manual size, lines, all lines, and we are considering numbers of elemental division for each line equal to 10. Okay, done. Now finally we need to go for meshing. Mesh lines, pick all, so it is meshed completely. Now we need to apply our boundary conditions, and it will come from loads, analysis type, new analysis. It is a static structural analysis. First of all we need to fix the left hand side, because it is a cantilever beam, it will be fixed at the left hand side. So define loads, apply structural displacement on key points. Let us select key point 1. Okay, now all degrees of freedom should be fixed. It is restricted to move in all directions. Okay, done. First boundary condition is applied. Now we need to apply load, and for seeing the load location we need to change the pattern of this one, 2 lines only. So plot lines. From this location to this location, we will be having uniformly distributed load of 1.5 kilonewton per meter, right? So structural pressure on beams. Let us select the box for selecting the specific beams or the specific nodes. We're starting from here. We need to select all the specific nodes selected. Okay. Now the thing is, uniformly distributed load is 1.5 kilonewton per meter, directly in the downward direction. Why? So it is starting from minus 1500 and finishing also minus 1500. Okay, done. So we have applied all the necessary boundary conditions as per the question. Now we need to solve it, right? So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so our result is okay. We can see our results from general post processing, right? Let us close it. General post processing, and first of all we need to read results from last set. Now we can create the elemental table. So element table, define table, we need to add it, and it is already told that for bending moment we need to depend on SMIS 2 and 15, and for shear force we need to depend on numbers SMIS 5 and 18, right? So let us take these numbers from here itself. From drop down menu we can select by sequence number, and from SMIS it will be 2, that is for bending moment. Apply. First one is made. Again repeat the process. By sequence number selected from drop down menu. SMISC 15, that is for bending moment. Applied. Now again repeat the process. By sequence number. SMISC 5, that is for shear force. Apply. And the last one by sequence number SMISC 18 selected. First two numbers SMIS 2 and 15 for bending moment, and SMIS 5 and 18 for shear force. Okay, let us close it. First of all we'll see the results in the form of list results. So list results, and we're going to see reaction solution, all items. You can see the total reaction is actually 2400 Newton at key point number 1, or at the left hand side it is 2.4 kilonewton, right? Okay, done. Now we see all the shear force and bending moment in the form of listing. So element table data, and let us select all the numbers from here itself. SMS 2 and 15 for bending moment, and SMS 5 and 18 for shear force. Let us see that. Now first two columns are actually representing bending moment, and the third and fourth column representing shear force. We can see all the bending moment and shear force data at the different nodes. We have created total 20 numbers of nodes, and each node we are having shear force and bending moment, right? So you can see the last part. Maximum bending moment occurs at node number 20, and it is 19.2 kilonewton meter, right? And at node number 1 we are having maximum shear force, it is 2400 Newton. Okay, so first one is providing maximum bending moment at node number 20. It is not maximum, it is minimum bending moment, right? It is minus 19.2 Newton meter. Maximum shear force is 2400 Newton at node number 1, right? Next to that, we're going to see all these results in the form of graphs. So plot results, can do plot line elemental response, and we're going to select specific lines for bending moment. It is SMS 2 and SMS 15. Okay, you see here minimum bending moment is 2880 Newton meter. So it is minus 2.88 kilonewton meter at the extreme left hand side at key point number 1, or you can say load number 1, right? Now we can validate this one with our actual results. Let us see the question paper itself. It is also showing the same thing. That is minimum bending moment occurs at key point number 1. It is 2.88 kilonewton meter, right? And it is exactly same what we got in our ANSYS mechanical APDL. Okay, right. Next one we'll see our shear force. So again, line elemental response, and instead of these numbers you can change it to SMS 5 and SMS 18. That will provide shear force diagram. Okay, now let us see this one. It is showing that maximum shear force is occurring at key point number 1, and it is ranging a specific distance. Its value is 2400 Newton, and at this location you can see it is 2133 Newton. Let us see the results from our actual question paper, and we can compare these things. Maximum is 2400 Newton, right? Let us see that again. Here also it is showing the exactly same thing. Maximum shear force is 2400 Newton or 2.4 kilonewton, and that is occurring at key point number 1, and it is ranging a span of 0.4 meter, right? Okay, so let us close this one. Now another thing we can do, we can see the animation of this cantilever beam. which is having some uniformly distributed load. First of all, we see the beam in the form of 3D. So plot controls, style, size and shape, and display of elements should be on from here. Okay, done. Now let's see the element, plot element. So you can see this is the beam. For better view, we can have the oblique view also. This is the beam. Now we can see the animation of this one from plot controls, animate, and we want to see deform results, right? And we want to see translation along y direction. So uy, let us see the animation of this one, right? And with decrease in delay, let us see the animation in a better way. See how the beam will be vibrating or animating. Okay, so let us close this one. With this one, we'll conclude our today's video. It is a very simple analysis of a cantilever beam with uniformly distributed load. And in this analysis, we found the shear force and bending moment diagram using ANSYS mechanical APDL, and that was validated with the answer obtained from theoretical results, and it was exactly same what we got in our theoretical results. So it is validating our results using ANSYS mechanical APDL. Okay, so with this one, we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.